Doc, with a request here from a student to review resonance for exam one. So let's go to the book. We'll go here with the downloads, and resonance is in chapter B. And let's check out what we have here. We're going to look at sympathetic vibrations, another word for resonance that you often see. And it has to do with a system that on its own, if you pushed it and let it go, it would like to wiggle. So always start with this kind of an arrangement where you have something that likes to wiggle or wants to wiggle. Maybe it's a glass that wants to vibrate. You know, if you flick it and click it and you hear a little tone, or it's a grandma in a rocking chair that rocks on her own. You know, she just push it once and then she go back and forth. This kind of thing. The standard sample I gave you in class is a ball on the end of a string, and this likes to wiggle. If you pull it back, it wiggles back and forth. So that's the way to get started, that there is a system that will undergo some kind of vibration. It's capable of undergoing vibration, and I say it wants to vibrate at a certain frequency. So hear this ball on the end of the string. If I pull it back and let it go, it wants to go at a certain rate, so many times per minute. Grandma on a chair, if you pull her back and let go, she'll want to go back and forth at a certain rate. So these systems that like to vibrate, there's a characteristics. The characteristics that they have would be you pull something away from equilibrium, like you pull a kid back on a swing. Say this is a kid on a swing here. Pull a kid back, let go, and then the kid starts out here at rest, and you let go. It gets faster and faster. Goes through the center, and then overshoots, goes to the other side, and stops momentarily and turns around and comes back. So that's the thing. Whether you're a let's say molecule in a glass that is going to move back and forth, or whether you're a grandma in a rocking chair or a kid on the swing, or let's say some kind of any bound system that wants to wiggle back and forth, you're ready to go. So once when you have that set up, you excite the system at the frequency it wants to go at, make it go crazy. That's the idea. And when you do that, you have the resonance. The resonance frequency is this frequency here where the peak is. Now in class, I demonstrate this, and I encourage you to take your shoe with the shoelace, and if you wiggle back and forth at a low frequency, very low frequency, you don't get much of a response. If you wiggle back and forth at a high frequency, you even have less of a response. But if you drive it in the center, with some magic frequency that it likes to go at, and you don't have to move your finger back and forth very much at all. In fact, keep it very, very small in your wiggling amplitude to be fair to all the frequencies. You will watch it build up and it will go crazy. That is resonance, also called sympathetic vibrations, that the system's in sympathy with what you are doing to it, and you get that big, big response. And then you might look through our examples. I gave you 10 examples of resonance, and try to find in each case the system that wants to do some wiggling like this glass, and then there's a driver. See, my hand, I drove it. Someone then comes along like the singer and sings the note that the glass wants to vibrate at. And since the glass is not designed for that kind of stress, if you sing, especially through the microphone, you can get a loud enough effect to break the glass. I wouldn't recommend anyone trying this without a microphone, although I've heard on YouTube someone has pulled it off. Same thing with soldiers walking across a bridge. The bridge may have some kind of vibrational modes, and by walking across a bridge, if all the soldiers should walk in step, they might get close to that frequency, have a big response, and knock the bridge down. So they're told not to walk across a bridge. So look through these. Here's another one where a bulb blows up at a concert. This bulb does have a frequency of oscillation in the glass. It's not designed to do that, though. So when it's driven by a horn playing in the right frequency, you actually can hear the tone that it bursts. So look through these, and you will master your resonance. And remember, the last one here involving the bridge is not a resonance, but it's a fun one to include with this discussion, as physicists thought for a generation incorrectly that it was.